This is a lesson about functions. What I'd like to do is to keep track of functions in terms of a set theoretic definition before we go to other ways of thinking about it. So I want to think about not the kind of a situation that you might be used to from an algebra course where you've got an interval on the real line and an interval on the real line determining a function as a graph. I'd like to keep track of the function first of all as a rule, explicitly matching up elements from one set of real numbers, x, with another set of real numbers, y. So x matched with y is the way that we'll think about what a function does. And what matters is that x values are related unambiguously, that's the unique element part, are related to, each x value is related to a unique element of y. That means that you can't have an x associated with two or more elements of y. That's really the only restriction. If you've got a situation where this rule is satisfied, then the set of elements that works as where the function's coming from, you might say, starting with x, those elements x are the elements of the domain of the function, and where they go is the range of the function. Each element in the range of the function counts as something that is an image of one of the elements that was in x. There is a good picture to keep track of this, which I think of as the pickled egg picture. Doesn't this look like a pickled egg? It's blue on this side, the outside of the egg, and if you cut it open you can see the yolk. But what's interesting about that is you could think about the set on the left as the domain, the x values, and you look at x values going to y values and represent that by drawing an arrow directly from the x to the y value where it goes. So this x goes to this y, this x goes to this y, and this x goes to the same y that the second one did. That's okay. The definition says that it has to be unique. That doesn't mean you can't use one over again. It means that you can't have one x going to two different y's. Two x's to the same y is okay. So if you look over here, the elements y in the middle part, I guess y stands for yolk here, those are the elements that are in the range of the function, and the ones that are out here are elements of the set y that are not in the range of the function. That's okay. So you can keep track of a function as a rule. Maybe it's given with a verbal description, or you can keep track of it here like a diagram. Another way to keep track is to explicitly list what is supposed to be associated with what. For instance, suppose you want to decide which of these relations are functions. Saying it's a relation just means it's a set of ordered pairs. So ordered pair 1, 1 means x1, y1. When x is 2, y is 4 in the second term of the ordered pair. x3, y9, x minus 3, y9. So an x value, a y value, and if you look to see if the definition of a function is satisfied, 1 goes with 1, 2 goes with 4, 3 goes with 9, minus 3 goes with 9. In each case, I have an unambiguous choice of what to do. With the x value, I know where it has to go. The fact that 3 goes to 9 and minus 3 goes to 9 doesn't hurt anything. Two different x values sharing the same y value doesn't violate the definition of a function. So this set of 4 ordered pairs defines a function. Just from that ordered pair as given, the domain would be the possible x values, 1, 2, 3, and minus 3. And the range would be the y values that arise as function values. That would be 1, 4, and 9. Since 9 is used again, you could just list that set of 3 elements as the range. Another example, 1, 1, 1 minus 1, 2, 4, and 4, 9. In this case, x equals 1 goes with y equals 1 from the first ordered pair. X equals 1 goes with y equals minus 1 on the second ordered pair. And that's a problem, because if I were given 1 and tried to apply this rule, I would not have a unique y value. It could be 1, it could be minus 1. And that ambiguity, that one or it could be either one, is what violates the rule part of what a function's supposed to be. So these two ordered pairs in this relation are enough to say that this does not represent a function. If you're fortunate enough to have that algebraic context of function where you're keeping track of elements of the domain and range, the x's and y's as points in the plane, and then your graph is maybe a line or a squiggle in the plane, then a reasonable thing to do is to apply the vertical line test. What makes that work is, if you think about a vertical line in the coordinate plane, a vertical line has a constant x value, and different points on the line represent that x value with different y values. So if a vertical line crosses a graph at 2 points, those 2 points represent one x value matched up with 2 different y values. That's the problem, and enough to say that the function definition isn't satisfied, and it wouldn't be a function then. So, for example, this ellipse, if you looked at the equation for an ellipse, you'd find a relation between x and y that does not, in general, give a single y value going with each x value. For this diagonal, for this vertical line, for instance, here's an x value. You could go up or you could go down, and whether you go up or down, you intersect the graph, and whether you go up or down, you pick up a y value going with this x value. That means if you tried to say this represents a rule that would associate a unique y value with each x value, this x value could go with this y, could go with this y. It's not unique. And that means that this graph does not represent y as a function of x. It doesn't represent a function. Let's look at one that does. What goes wrong here? Not a function. Let's look at one that does. This graph is, no matter where you draw a vertical line, that line crosses the graph at 1 point. So each x goes with a unique y, each x goes with a unique y, no matter where you draw it, a unique y. And that's what it takes to have this represent the graph of a function. What else could a function look like? Well, maybe back to that algebraic representation, you're used to thinking about a function as an equation. Suppose you've got a rule like this. F of x is 2x squared plus 5. What that says is that when you start with an arbitrary x value, you calculate the y value, the function value, by taking the x value, squaring it, doubling the result, and adding 5. You can do that for numbers, so that if you try to do it for 3, you're going to square that number, you're going to double the result and add 5. Square 3, double the result, and add 5. 3 squared is 9, times 2 is 18, plus 5 is 23. Or you could apply it to another algebraic expression. If the rule applied to x is that x squared times 2 plus 5, the rule applied to this more complicated thing, x plus h, is that complicated thing squared, doubled, and add 5. So now it's an algebra problem to multiply this out. Remember how to FOIL to get a perfect square of a binomial. X squared plus 2xh plus h squared. That's the square. Double it. Add 5. And now you can combine like terms and distribute the 2 out to get an algebraic expression that represents this function, this rule applied to the complicated algebraic expression x plus h. Makes as much sense to do it with that as it does to do it with a number. Let's think about what happens for a domain of a function, that's the set of x values that works, if you're fortunate enough to have a function given by an algebraic rule. Well, the values that the rule makes sense for are values which you can do the arithmetic for. Now you should just think about what can go wrong with arithmetic of real numbers. You've probably had drilled into you two examples that you're not allowed to do. One is you're not allowed to divide by 0, and another is that you're not allowed to take the square root of a negative number. So those are examples of the kinds of things that would affect what the domain of a function given by an algebraic rule would be. How about this first case, a polynomial? G of x is 3x cubed minus 5x plus 1. Nothing to do there about dividing by 0 or taking a square root of a negative number. I don't care what real number x is, x cubed makes sense. Times 3 again makes sense and gives you an answer that's another real number. Minus 5 times x is fine, and adding 1 doesn't hurt anything. There's no number you can't use, and that means all numbers you can use. So you would report the domain of this function, the domain of g of x, is the set of all real numbers. How about this case? S of t is 4 over t minus 1. It looks like t is the variable that I'd be interested in. And think about what could get in trouble. Well, if you're trying to divide by 0, 4 over 0 is not defined as a real number. So a value for t that makes dividing by 0 happen is a value you would like to exclude from the domain of the function. That's the only value you need to exclude. So the domain of S would be all t's different from the one that makes trouble. All t's different from 1. One more example. How about a square root? H of z is the square root of z plus 2, for instance. What's the domain of h? Well, again, what I want to be careful of is to make sure my arithmetic as real number arithmetic makes sense. So I want to make sure I'm not taking the square root of a negative number. When does that happen? I want to make sure that z plus 2 is not negative. I want to make sure that z plus 2 is bigger than or equal to 0. That happens when z is bigger than or equal to minus 2. And hence, the domain of the function h is all z, set builder notation, set of all z such that z is bigger than or equal to minus 2. So a function could be given as a rule, just some kind of a verbal description. A function could be given as an explicit set of ordered pairs, the variables being linked by the rule. A function could be given by an algebraic expression. A function could be given as a graph. How about this? There's no way. This is a complicated behavior. It goes up, it swoops down, it makes some kind of a semicircle here. You're going to have a hard time coming up with a single algebraic equation that would describe what the graph of this function looks like. And yet, it makes perfectly good sense to look at the set of ordered pairs represented by points on this complicated curve as being x and y values related by a function relationship. This thing satisfies a vertical line test, so it represents a function. As long as it represents a function, you could look at particular values. If I say, okay, suppose x is 2, what's the function value? So you go to 2 and see the point above 2 is a point with coordinates 2, 3. So the function value y is 3 when x is 2. And you can do that point by point for points on the curve. Question might be, okay, what's the domain and what's the range? Well, the domain, remember, is the set of all possible x values that work. What happens over here, the graph is silent about. There's no points there. And what happens over here, there's no points. The only x values that make sense by this graph are values that start at 0 and that go over to 10. So the domain is the set of numbers in that interval from 0 to 10. How about the range? The range is a set of y values that make sense. And if you look, there are several values for y that work with a particular, for different choices of x, but the very smallest y value that ever works looks like is minus 3. There's no y values less than minus 3, and there's no y values bigger than 3. I kind of imagine a light shining straight across here and looking at the shadow that this graph casts on the y-axis. It goes from minus 3 to 3. So the domain of this function would be the interval from minus 3 to 3. Say domain, I meant range. The y values that work are the range from minus 3 to 3. So we pick up domain and range by analyzing a graph as easily as if we were given a function in terms of an algebraic rule or as an explicit table or set of ordered pairs.